I have a soft pillow in the shape of Saturn here, or something nice, and I've got this big lump of iron in the other hand, and they're about the same size, but they're very different. And trying to understand how they're different is key here. The two objects are, well, first of all, they're different in density. That's probably the most obvious thing from the outside of them that I can tell, that there's more atoms in this for its size than there are in this, and it actually turns out that those atoms of the iron actually have more protons and neutrons in them. It makes them heavier. But that having more stuff in this space actually has an effect on how they behave when I handle them. Having more atoms here, and having those atoms being bigger atoms, it means that this becomes quite difficult to handle. Whereas this, I can chuck around. I would probably break, myself if I tried to chuck around this. I can give it a go. Right, this is really difficult to chuck around because it has so much mass. So, what is this thing, mass? Well, mass is a measure of how resistant to acceleration an object is. If you have a lot of mass, it's probably because there's lots of atoms in there, and that those atoms could be quite heavy atoms. Those at the bottom of the periodic table, for example, they have more mass than the ones at the top. If your density is high, then you also will probably have a large mass for your size. But look what happens here. If I take this, what do I mean by accelerate? Well, if I start to move this to the left and to the right, like this, again and again and again, I could do this all day because this does not have a lot of mass. When I take it to the end and then I accelerate it back again, I'm continually accelerating, and it takes very little force for me to do so because it's so low in mass. But if I try to do it with this is high in mass, and me moving it to the side, instantly you can see it is taking from a force, and if I did this for very long, I would probably break myself. If you have more mass, it's harder to accelerate you. It takes more force to keep accelerating this backwards and forwards. So let's talk about and consolidate those ideas about mass. So all of these different elements, and you can see that they're arranged here in mass order. The hydrogen up there has the lowest mass of any of the atoms, and that's because its basic ingredients are just a single proton. And then the next one, helium, well, that is made out of 2 protons and 2 neutrons. And you can see that therefore the mass, given that all of these basic building blocks contain a set amount of mass, you can see that helium is basically going to be 4 times heavier than hydrogen. And something further along, further down, is going to have even more. So you can see that the mass of an object actually depends on what it's made from. That something that is made out of a very light element, like hydrogen, is going to have a lot less mass than something made out of something very heavy, like lead. Where's lead? It's here somewhere. I always struggle with it. Where is it? Lead. Lead. Where's lead? No one ever knows where lead is. Huh. Lead. There we go. Just there. Ha. So you can be a different mass by just having a different number of protons and neutrons, being a different element. And that is the difference between these two here. But there is a second way in which you might have more or less mass, and that is just by having more or less atoms. You see here, I have got less mass than I have there. And that is just because there are more atoms there than there are here. So the two things that affect how much mass something has is what element it is and how many of those atoms there are. In physics, we call this property of mass one of the most fundamental things that we can even think about. The symbol is lowercase m, and the units are a kilogram. Now, what does 1 kilogram represent? Nothing really. it was arbitrarily decided that a lump of metal should equal 1 in the units of mass, and that they called the kilogram. Now in physics we use kilogram as the base unit of mass, but in chemistry, because chemicals are using much smaller quantities, they're more likely to use the gram. And here is an important conversion that you need, that 1 gram is equal to 0.001 kilograms, and 1 kilogram is equal to 1,000 grams. Now it is possible to measure my mass on some scales. So here we go, on I get, and you can see, oof, 78 kilograms. Now, mass, being connected to how many atoms you've got and what element those atoms are, is always going to have a fixed value. Now, that means that wherever you are on the surface of Earth, or high in the atmosphere, or even in space, it is still going to be just as hard to accelerate that mass and change its motion as it is anywhere else. So it doesn't matter where you are, the mass is always the same. I would still be 76 kilograms on the moon. Now, a really curious thing about these atoms is they actually attract each other. Now, of course, solids hold together because of the attraction of the charges, but even if they were slightly far apart and not within range of each other's charges, there would still be a slight attraction between them. And this is the force of gravity. All atoms in the universe are attracted to all of the rest of the atoms in the universe. And what I can see here between this bunch of atoms and that bunch of atoms is that there is going to be a force of attraction between them. And the size of that is going to be dependent on just how much stuff there is here and how far apart they are. Now, if you get close to a very large object, then your atoms are going to be really strongly attracted to that large object. And this creates the force that we know of as weight. You see, when we stand on planet Earth, the attraction of this mass to the Earth below becomes so great that we have to provide forces of push to support this against being pulled down with gravity. The amount of force we push up to keep it stationary is equal to the amount of weight acting downwards. So how do we treat weight? How do we make sure that we don't confuse it with mass? Well, weight is given the symbol in physics of capital W, and it is a force. Now, like all other forces, the unit of force is the Newton. If I have more mass, there's more there to form an attraction with the Earth. And so therefore the force that exists between them is going to be higher. More mass, more weight. And so what you can see is that there's got to be some sort of formula that links these two together. More mass, more weight, it must be directly proportional. This is the formula that you'll need to use. The weight is equal to the mass of the object multiplied by the strength of gravity. And we call G, the strength of gravity, is the gravitational, wait for it, field, I've not finished, strength. On Earth, the gravitational field strength is equal to 9.8 newtons per kilogram. This means that my mass must be multiplied by 9.8 to tell me what my weight is. It also means that those slotted masses of 100 grams each are approximately 1 newton each. That's handy, isn't it? So if I was 76 kilograms, I would expect to be, roughly speaking, just less than 760 newtons. So let's measure my weight. So look at this. On the left-hand side, I have some weighing scales that take my mass, and on the right-hand side, I've got some weighing scales that measure my weight. And I step on here, I'm expecting to be, woo! These aren't calibrated very well. It's showing that I'm 1,000 newtons. Jeez, I did not think I was that heavy. But an important difference between this and this is they're both really weighing me. Both of them are measuring my weight, the force between me and planet Earth. The scales have been squashed between the two. But what's happening is, through that equation, the one that's reporting kilograms is actually taking my weight, dividing it by 9.8, and then reporting how many kilograms of mass I have. If your scales at home report newtons, which is highly unlikely, then they are in fact weighing scales. But if they instead report kilograms, they're not weighing scales, they're massing scales, which is just a thing I invented 3 seconds ago. So if we think about the solar system, each of these objects in the solar system has a different strength of gravity, depending on how big the planet is and how dense it is. On Neptune, the strength of gravity is 11 newtons per kilogram. This means that you would weigh just slightly more on Neptune than you do on Earth. Uranus, however, you would have a gravity of 7.7 newtons per kilogram. It means that if you're on Uranus, you would actually weigh less, which is surprising considering it is a bigger planet, but its density is actually less than the Earth. But going further in the solar system, a planet that is very, very large, but still very, very low in density, is Saturn. The gravitational field strength on Saturn is 9 newtons per kilogram. You would weigh less on the surface of Saturn than you would on planet Earth. But of course, the giant of the solar system is Jupiter, with a gravitational field strength of 22.9. You would be very, very heavy on Jupiter. The inner planets, well, on Mars, the gravity is 3.72. On Earth, it is 9.8. On Venus, 8.6. And on Mercury, 3.7. It means that to lose weight, you should all move to Mercury. And one final thing, on the Moon, the gravitational field strength is 1.6. Now that means that the Earth's gravity is about 8 times stronger than the Moon. It means that on the Moon you could jump 8 times higher than you could if you were on planet Earth. The weight of something determines whether or not it will sink or float. I have 3 balls here. This is a really heavy one, this is in the middle, and this one is obviously a balloon, so it is really, really light. They're all about the same volume. So, though this one is the heaviest, it has the largest weight, that is because it has the highest density. Now, what I have here is a box that is full of those sort of like polystyrene beads that you get with packaging. And I want to show you what happens when I place these 3 different balls in this box. So come on closer and have a look. So the first one I'm going to put in is the balloon. And you can see that no matter what I do, I cannot get the balloon to go under. It is still on top. That is because the polystyrene beads are heavier than the balloon. But if I made a polystyrene bead the same size as the balloon, the polystyrene beads would be heavier. The density of the polystyrene is greater than the density of the balloon. What if I try a slightly more dense object, you can see that this is almost neutrally buoyant. It's sinking sometimes, but then again it is coming to the surface at others. So with this is about the same density as the polystyrene. It means that for its size, this weighs the same as the polystyrene. What about the metal ball? Let's do it. Oh, where's it gone? It has sunk without trace. In fact, it's so much more dense than the polystyrene. It has sunk straight to the bottom. That it, for its size, didn't weigh as much as the water, in this case the polystyrene, that it displaces right down here at the bottom. And the same is true for water. So in this case, this balloon is, it weighs a lot less than the water it will displace. So if you consider the water level is here, normally, and water being a liquid, it takes the shape of the container. But now we submerge an object in this water. So an object is going to go in here, and let's say, for example, on this simple example, that it has exactly the same density as the water. So it floats neutrally. It's neutrally buoyant. None of it is sticking above the water level. Then what happens is the water level goes up as a consequence of the object being in the jar. So some of this space here is now occupied by the object. So where the water was is going to have to go up instead. And it means that some of the water is displaced above the original position. Now that means with this displaced higher up, it means that its weight acting downwards onto the water is causing basically the force of upthrust, equal and opposite, to act on this object. The weight acting down is squeezing and pushing up the object. But there's a subtlety here. What determines the height in the water that an object will float at? If you see this, half of this is underwater and half of it is above the water. Well, when the iceberg is in the water, some of it is underneath the water and some of it is above the water. And what you can see here is a diagram of that. Now, the presence of this iceberg has displaced some of the water level has risen. The weight of that water being displaced acts down and pushes up the object. So the level of the water on the object, well, that is determined by this. When the weight of the water displaced equals the weight of the object, then there is a balance. Now the weight of the object is never going to change. But of course, the more as we lower this into the water, the more of it that is underwater, the more water there is displaced, until it reaches a point where the displaced water is equal in weight to the weight of the object. At that point, no more of the object is going to go underwater, because if you push more of it under, then what starts to happen is you displace more water, which means that the upthrust force becomes greater than its weight and it pushes it up slightly. It reaches a balance where the force of upthrust equals the weight of the object. And then the upthrust here is equal to the weight of the displaced water that's causing it in the first place. So the upthrust is equal to the weight of displaced water.